Hi guys! So I'm Olivia and I'm going to talk about metallic bonding. And as you can see, I attempted to make, I just look like a clown, but I did like the full face of highlighter on my face to look like metallic bonding, but I look like a clown. So let's jump into the video about metallic bonding. The first thing you need to remember is that you can never just have one metallic bond. You need to have a number of atoms to share their electrons, so therefore they're sharing bonds. This is best shown by the electron C model. The main thing to remember about metallic bonding is that we have delocalized electrons, which are electrons that have the freedom to move. In the electron C model, electrons are constantly drifting around each other. This model displays how a lot of the properties we have, such as conductivity, malleability, ductility, and low volatility, are possible. Keep in mind that the transition metals have a lot of unpaired electrons in the d orbital, which is why the electrons have the freedom to move. The reason why metals can conduct electricity and heat is because electricity is simply the flow of electrons, which occurs because they are delocalized. Now, when you hit a metal and it flattens out, the metal is displaying how malleable it is. On the microscopic level, you are basically hitting the atoms, which are able to slide past each other. This is how you can get something like a gold leaf. Now, when you pull something apart but it stretches rather than breaking apart right away, that is the metal's ductility. And this is because the free-flowing electrons can slide past each other. A metal's low volatility is due to the huge attraction between the negative charge of the electrons built up with a positive charge. Since there is such a strong attraction, it is difficult to remove just one electron, which is why it is hard to make a metal into a liquid or a gas. Now, to look at something such as the melting point, we have to look at the shell model. If we look at the fourth period, moving down the period increases the electrons, which means it is harder to melt, or so you'd think. The pattern is consistent until chromium. Since chromium's 4s is completely filled, it has a lower melting point because it is more stable and there is less free electrons. Overall, when the transition metals have all of their orbitals filled, there will be a lower melting point than the rest of the pattern.